Hello everyone, my name is Ferishte Sadeghi and today I'm going to talk about our recent work with Sergey Levin. The title of our paper is Real Single Image Flying Without a Single Real Image. In this work, we developed CAT to the power of 2RL, a flight controller for collision avoidance via DeepRL that, although is entirely trained in a 3D CAT simulation environment, it can perform collision-free flight in the real world. But before getting into details, let's start by seeing why is this important and what is the actual problem that we are solving? Well, for sure we would all like to have mobile robots that are able to move around in our buildings for doing different tasks, such as transporting packages or providing dynamic surveillance for better security, and of course many other applications, such as capturing the virtual tour of the building for VR and AR. For all these applications, the robot should be able to avoid colliding with different obstacles in the indoors, such as walls, furniture, and so on. Amongst all different types of mobile robots, we are most interested in the flying robots, since they can provide exceptional functionalities by not being limited to moving on the ground surfaces. But of course, the algorithm that we have developed can also be used for other types of mobile robots, and it's not just limited to drones. Okay, so we would like our flying robot to have a collision-free autonomous flight, such as this. And in fact, this video is captured while a drone is flying by our proposed CAT2RL controller. On the top right, we show the input to our controller, which is single RGB images from the onboard camera. Our controller gives out control points that are shown as red dots to specify the flying direction. As you can see, CAT2RL can successfully fly the drone in different scenarios such as corridors and sharp turns, or flying it up the stairs and through the open spaces. I would like to emphasize that our controller haven't ever seen a single real image at the training time. But why is this problem hard? Well, designing controllers for flying robots had been previously studied in the robotics and computer vision. The previous approaches have tackled this problem by 3D estimation mapping or learning approaches and a combination of both. To do 3D estimation mapping, many prior works have looked at using depth or stereo camera for SLAM and 3D perception. And in the learning approaches, previous works have used human demonstration or teleoperation for collecting data to provide some sort of supervision for learning the controller. However, 3D estimation mapping is a pretty challenging problem, especially when using monocular camera. And also adding additional sensors, such as depth sensor, imposes cost and energy overheads for the robot platform. On the other hand, the human collected data is expensive and tough, and such data will have limited quantity and low diversity. This will cause the learned controller to suffer from limited generalization. To overcome the mentioned limitations, and given the advances in the DeepRL for learning motor commands directly from pixels and only using environment feedback, we use DeepRL for learning our controller. So back to our problem. We have different corridors and we would like our drone to learn how to fly from its own experience. Alright, we'll let our drone fly. It may collide with things and it will be penalized, or it may move forward by which it will be rewarded. It will continue doing this on and on in millions of iterations until it eventually learns how to fly. And at this point, we would be basically done. But wait, I said millions of iterations. The bitter fact is that this is not quite feasible in the real world, because you really cannot let the drone crash into things. It will break itself and also will make lots of damages. Furthermore, DeepRL needs huge amount of data, and this approach would be very slow and cumbersome to collect such data, which will again lead to having limited data and poor generalization. A promising avenue for addressing these challenges is to train policies in simulation, and most recently this has gained increasing amount of interest. Different environments are made available, such as Atari games, Mujoku, Wisdom, Minecraft, and of course hot from the oven, DeepMind Lab and OpenAI Universe are made available. Learning in simulation is great because it gives us a lot of data for training with high speed, and by the flexibility that it provides, we have the freedom to develop better algorithms, which is just great. However, a little bit of the dark side is that by learning in these somehow cartoonish environments, our algorithms suffer from a reality gap. And of course, more recently, different works have tackled this challenge by doing transfer learning of some sort. In our work, we also use simulation to learn the flight controller. We designed a collection of synthetic 3D hallways to generate large datasets, especially designed for the task of hallway following and navigation in the real world. Our design hallways have a variety of floor plans and are rendered with variable furniture placement, different lighting conditions, and diverse textures. By highly randomizing the rendering settings of simulation training set, we show that we can bridge the sim-to-real gap and train a collision predictor that generalizes to new unseen environments with substantially different appearances from the training scenarios, as well as real world. As a result, our controller addresses the high sample complexity of deep reinforcement learning and avoids dangers of trial and error in the real world. As I mentioned before, the input to our method is single RGB images without depth from a monocular camera mounted on the drone. And to learn a general collision avoidance predictor, we developed a model-free DeepRL algorithm inspired from fitted queue iteration. We start each episode by placing the agent at a random location with a random orientation. The input image is discretized into a grid of bins. Each bin corresponds to an action, such that the action at time t is simply the choice of the bin, and the actions are taken based on the current policy. Once the action is chosen, it will be transformed into a velocity command to move the camera forward in the simulation. We simulate multiple rollouts for flying in different directions, and this mechanism provides capability of parallelization for efficient simulated training. Some of the flight directions may lead into collisions, and collisions are assumed to end the episodes. We also have a finite horizon h. Using these multiple rollouts, we evaluate the return of each action, which corresponds to the probability of collision, and here C denotes the discounted expectation of a collision event. This policy evaluation provides us with a dataset of observation, action, and return tuples which we use to update the policy. Having multiple rollouts of different actions starting at each location, we end up with a dense map of collision probabilities for each observation. And we use a fully convolutional neural network to learn predicting this dense collision probability map. We evaluated the generalization capability of Cat2RL and a transferred domain with realistic textures on floor plan, which is a close proxy to the real world. This environment had been entirely unseen at the training time. Our controller can maintain a long collision-free flight in this building and performs better than the baselines. We also tested on a set of complex synthetic floor plans that are not seen during training. Our simulated evaluation shows that our method outperforms several baseline and a prior work. We also quantitatively evaluate our RL-based controller in the real world in two different buildings and compare it with a supervised free space prediction approach. Our RL-based controller experiences collisions almost 50% less than the supervised free space predictor. Finally, we qualitatively show the performance of our flight controller in a number of various real scenarios for navigation through hallways and avoiding general obstacles. To conclude, we showed that training on randomized simulated scenes produces a model that can successfully fly the drone and avoid obstacles in the real world. But of course, this approach requires manual engineering to design suitable training environments, which would be a challenge to be considered in the future work. For the complete flight videos, please check Cat2RL GitHub IO page, and thanks for your attention.
Wonderful. Are there any questions?
I can answer the questions.
So with respect to the previous talk where the vision was more separating control from perception. I was wondering, what do you think the benefit of simulation would be to counter that argument? Because in my experience, there's many papers that came out at computer vision conferences this year, like Virtual Kitty, Cynthia, and Thor, where they use photorealistic virtual environments to learn perception, so not control, not reinforcement learning. And so they have also this vision of separating perception, because in this virtual environment you have all the ground truth, so you can have everything you want to know about perception. So,
question. One is, should we have photorealistic rendering, and the other one is, should we also deal with control as part of the learning process? Now, I should say that in this work, control can mean two different things. It can mean sort of choosing a motor command, or it can mean choosing the lowest level motor command. In this work, the quadrotor has an onboard flight controller that takes in a velocity command and uses that to determine the rotor speeds. So that part is actually, it's just the onboard controller the vehicle has. So the neural net is choosing a slightly higher level command. In regard to the photorealism, I think one of the lessons for us from this work was that photorealism is perhaps less important than diversity. So the environments that Fresha showed in the talk were not very realistic, but they were extremely diverse. And I think that is in many ways key to the generalization ability.
Yeah. I would agree exactly with that comment. We organized a workshop at ECCV, and the conclusion of that workshop was not how to generate photorealistic data, because actually we're quite good at this, was more what to generate. So the conclusion was the same as what you just said.
Okay, I think we should move on to the next speaker.
All right, thank you, Sergey and Fereshta.